Well, thank you very much. It's really hard to give this talk, to be honest. Andre played such a big role in my life, and nothing foretold what happened. And I was looking forward to this conference, looking forward to seeing him again and discussing with him. And it was such an anticipation, and now we have to basically really speak at an memorial conference. So I'll try to do as much as I can. My talk is, in some sense, in a deeper sense, is about symmetric groups on fundamental level. But formally, it's called categorification of supersymmetry. So part of representation theory and of other areas of mathematics is about representation of superstructures, such as Lie superalgebras, for instance, associative superalgebras, and so on. It's based on certain twist of commutativity. To write the simplest formula is, of course, this formula, is AB equals -1 to degree of A, degree of B, times BA. So this is known as supercommutativity. And the point is that supercommutative algebras are just as good as ordinary commutative algebras. That's one point. And the other point is that many people, so this was bugging many people, as it bugged me for a long time. So something has happened, we were given something which we don't fully understand. We're given a twist which works just as good as if there was no twist. But it's not clear somehow what it is a part of. So it's there are various attempts to generalize this, and again, the result was that it cannot be generalized in any meaningful way. So let me discuss a little bit about the meaning of this. Let me call this the Cazul sign rule, for lack of better name. So of course, at the next level, we can say that this is a part of symmetric monoidal structure. If we have z-graded vector spaces, have the category of z-graded vector spaces over a field K. So it has tensor product, the usual graded tensor product. And we have symmetry, which is homomorphism from V identification from V tensor W to W tensor V. Identification R, which is given by the same formula. So V tensor W goes into -1 degree of V, degree of W, W tensor V. And this makes this into a symmetric monoidal category. Which in itself is a categorical analog of the concept of commutative algebra. Which is categorified. So you see here, if we look at this very roughly, we see commutativity. V tensor W is the same as W tensor V. And the more advanced point of view is that on the categorical level, we have commutativity again. So, and that's why everything that can be done for ordinary commutative algebras, Lie algebras, and so on, can be, in principle, extended to super commutative situation. So it can be either this or Z2 graded one. Because in order to write this, we only need reduce mod 2. So now let's try to understand what's the minimal data needed to write this sign rule. So we were given this kind of gift, like something fell from the sky, and we don't understand where it came from. So let's try a little bit to put it into a context. So in order to write this, we don't really need the full category of vector spaces. It's already, this phenomenon is already seen on one-dimensional vector spaces. Let's consider the category 1 vector, KZ. So there's a graded vector space of which total dimension 1. So one dimension graded space. So already suffices. Now, in this category, it's of course much simpler. So in this category, all objects are invertible with respect to tensor product. So this is an example of what's known as Picard category. So if we consider the category for this one-dimensional graded vector spaces and their isomorphisms, then it's an example of a Picard category, which is a symmetric monoidal category P. So symmetric monoidal category. With everything invertible, all objects and morphisms invertible. So any such category, so a typical example is the category, the name Picard category comes from the Picard group. The typical example is the category of line bundles on an algebraic variety. But this is another example. To such category, we can associate two groups. So one group, let's call it pi 0 of P, is the set of isomorphism classes of objects of P. Well, we assume that's a set with respect to the tensor product. So it's a group because we assume that everything is invertible, and it is an abelian group because symmetric monoidal category. And another group, let's call it pi 1 of P, it would be the group of automorphisms of the unit object. And in this case, it's automorphism of any object. So in this case, we have like a smaller thing which already contains this little gift from the sky, this Cazul sign rule. So in this case, in this example, we have pi 0 equals z, because a one-dimensional graded space can be situated in some degree. This degree is invariant. And pi 1 is the automorphism of the vector space, is the multiplicative group of our field. But now, again, this is not the most minimal thing, because what we really need to write this rule, we only need plus minus 1. So the true sign skeleton would be a Picard category where this thing is cut down to plus minus 1. Let's call it sign skeleton. And let me call it S. Well, in order to do this, we can consider, for instance, here it's one-dimensional vector spaces over a field. Well, we can reduce to something when there is only plus minus 1 in the multiplicative group. We can say one-dimensional free modules over Z. For instance, let's do it like this, one vector. Graded objects which are simply free rank 1 modules over Z. Yes? Then pi 0 equals Z, and pi 1 equals plus minus 1. So this is the minimal thing we need to write. So, and this is a Picard category with such properties. Now, the fact that super sign rule cannot be generalized, one way of saying this is that this is the minimal Picard category generated by one object. So the first fact, again, most of what I'm saying is in fact folklore. So fact 1. S equals the free Picard category generated by one object. And this object would be L. I call it L. Well, it is this thing in degree 1. So let's in this setting, it would be the abelian group Z sitting in degree 1. So if we just say, like, we generate a free group by a set of generators, we can generate a category by a set of generators, which means it has an object, identity object, it has object L, it has its square, it has L dual, which is L inverse, L minus 2, and so on. But because it should be a symmetric monoidal category, the data of this, so what are the morphisms of this? Would be simply, we need to introduce, for instance, this one, from L tensor L to L tensor L. And this element squared to 1. And everything else is expressible through this by the axioms of symmetric monoidal category. So this, again, once we think of it, it's a relatively obvious thing. So this sign skeleton is simply the free Picard category generated by one object. And that somehow explains the appeal of the sign rule, because it's the maximal way we can push it. So this is the axioms, and this is whatever the axioms imply. This is a possibility of something of order 2, and we account for this possibility by putting there plus minus 1. So now I want to look at this from a slightly different point of view, discussing so-called Grothendieck dictionary about Picard categories. So in his manuscript on stacks, and in other writing, Grothendieck suggested, and by now it is, of course, a theorem. It is not, if you put this, formulate it, it is not a very hard theorem, but it's a suggestive theorem, that Picard categories should be considered as the same with respect to appropriate equivalence as objects called alternatively spectra or stable homotopy types, or stable homotopy types, or infinite loop spaces. With particular type. So this is an object from homotopy theory, something which has homotopy groups, but with only two homotopy groups, with only pi 0 and pi 1. So pi 0 in classical topology is a set of connected components, and pi 1 is the fundamental group. So that in this situation, the groups defined like this correspond to homotopy groups in topological sense. And in particular, this S, which we now view as a free object, should correspond to sort of free stable homotopy type, and this something corresponds, let me write like this, which I called S truncated in degree 0, 1, and S is the stable homotopy type, which is known as the spherical spectrum. So its homotopy groups by I of S are the stable homotopy groups of spheres, which is by definition pi I plus n of Sn for n large, n greater than I. And this is the fundamental structure in topology of which we can observe the low-dimensional manifestations in a very elementary way. So let me write those stable homotopy groups, so low dimensional pi I stable would be like this. So if it would be I, those here would be pi I stable, would be 0, I go 1, 2, 3, and I won't go beyond 3. So in dimension 0, it is Z. In dimension 1, it is Z mod 2, which is exactly what we have here. So which is in our identification is plus minus 1. In dimension 2, it's also z mod 2. And in dimension 3, it's z mod 24. And it's known very, very, very far in that direction. Now, on this scale, so every box in this table has some moniker. We can sort of attach a tag to this, explaining which meaningful mathematical concept corresponds to this. This corresponds to dimension of a vector space, or cardinality of a set. This corresponds to the sign of permutation, or determinant of a matrix. So sign of permutation is something which appears when we start permuting several odd variables here. This corresponds to spin, because we'll see this corresponds to central extension of symmetric group. And also spin n to ON. And this is sometimes called string, because it's related to phenomena in string theory, and that z mod 24 has many interpretations. So what I was saying is that usual super formalism just exploits only the first two layers of this tower. Yeah.
Are we supposed to be able to see eventually these higher guys inside S?
No, we want to get the goal is to expand S a little bit, so that's to put those higher guys there. So that's just a truncation. So that's a usual super. So that somehow the idea is to incorporate better truncations of this bold face S. So we sort of we can say what should be higher supers. So try to incorporate more of S and pi I stable. Now let's see, where am I here? Yes, in particular, so this is just a part of Grothendieck dictionary. His whole point was that if we pass from categories to higher categories, we should be able to capture more of homotopy groups, and in particular more of this spectrum. So again, invoking or quoting Grothendieck. So if we pass from categories to two categories, which I won't do fully, I won't do this fully in this talk. I will just do some consequences of this point of view. Pi 0, pi 1, pi 2, and so on, as much as it's possible to formulate in elementary way. But in particular, a quite elementary object would be the next one. Let me call it S, simple S 0, 2, would be the free Picard 2 category on one object. And it would be desirable, I'll show how to do the first steps of this, to incorporate this into some higher superformalism. And in fact, some part of superrepresentation theory is already sees the traces of this. Incorporate into superformalism. What time is it? Before doing this, let me Yes. Yeah. Well, as I said, it has one object. It has some data. First of all, it presumes that we write the data of all the natural isomorphisms and connections within them. And then we generate the category to have this one object is tensor powers and all the isomorphisms and whatever they will produce. So this is the point of view of Grothendieck, that whatever they will produce will automatically give us this.
So it is defined by universal property?
Yes, defined by universal property, yes. But this is an object which can be defined in an elementary way. This is not something we have to invoke some transcendental construction. This can be read. Yeah? So in particular, in this category, there is, so maybe I'll just say one more thing about this table. So there is a coincidence here in this table. So this part is the usual supers. But we also can look at this part, which we consider there is actually coincidence. So if we consider truncation of S in degree 1 and 2, it will be something with pi 1 and pi 2, and take the loop space. It will be the same as S truncation of S in degree 0, 1. And we sort of reduce that Z mod 2. So there are two appearances of the same thing. Or in other words, if we consider this Picard category, then automorphism group, and now, in fact, not the group, but a category, S 0, 2 of one object, is the Picard category, is identified with the Picard category, category S mod 2, which is the category of Z mod 2 greatest vector space. This is by itself kind of interesting and sometimes helps put things in perspective. Now let me, where am I? Let me discuss briefly attempts. So there has, of course, in the subject can be several attempts of generalizing superformalism by introducing different types of signs, and not really signs by factors. Let me review this. So attempts of generalizing. Supers, I mean this point, this approach. So, and there is a result known as theorem of Nekludova. And the related theorem of Singh, who was a student of Grothendieck. Not completely to the same. So so what does come to mind naively? So suppose we want to replace this rule, this Kazul sign rule. And let me here do it more concrete. Well, we can say that we have an abelian group gamma, and we have a bilinear form from gamma cross gamma to k star, which is antisymmetric. So then we can consider the category of greatest vector spaces. And there is, with the ordinary tensor product, and again we have this rule, V tensor W goes to C of degree of V, degree of W, W tensor V. Or on a more abstract way, we can start with a Picard category P. And so it has pi 1, and consider a map from pi 1 of P to the multiplicative group. Then we can consider the category, let's call it vect Kp, which is simply the category of functors from P to vector spaces. So also becomes symmetric by a similar formula. So one can write it without appealing to this. So it becomes symmetric. Now here, of course, so let me see, right here it becomes symmetric. Now here, of course, we can introduce some equivalences. There's obvious equivalence. So C will be replaced by C prime, and we can write C prime of alpha beta equals C of alpha beta times H of alpha beta times H of beta alpha inverse, the cohomology. And this has an effect on algebras, so on commutative algebras. It says that we introduce new multiplication, A star B equals H of degree of A, degree of B, AB. And then Nekhludova's theorem is that any generalized commutative superalgebra after equivalence and after regrading becomes ordinary superalgebra. Nekhludova's theorem. So any C commutative algebra is equivalent after regrading to usual supercommutative one. And to compare this with theorem of Singh, this is simply a classification of such Picard categories in terms of pi 0 and pi 1, which means that P with pi 0 equals gamma, pi 1 equals B, two abelian groups, are classified by such similar clearly sets of data, C gamma cross gamma to B now, up to equivalence. Equivalence, as I explained here. This part 1. And part 2, so each such C is uniquely determined by data, which is essentially of order 2. Each such C, each such C modular equivalence is determined by a map Q from gamma to B, with Q of gamma is simply C of gamma gamma, which is of order 2 because and quadratic. So if C was bilinear, this is quadratic in certain obvious sense. Quadratic with respect to additive structure on this and this. So this again explains the fact that we basically in this situation we cannot go beyond plus minus 1. And it's not wise to try to push this in this direction anymore. But it's interesting to push it in the higher direction where we'll see we're actually getting something. Let me discuss a little more. Let me call this part the central extension of symmetric group. So I will, in fact, this pi 1 stable can be written as H1 of Sn, because it's a sign of permutation. Pi 2 stable for larger n, actually for n greater than 2, pi 2 stable is H2, and pi 3 stable is actually H3 for n large enough. Of Sn. So if you try to look at the commutativity, so in the naive way of comparing signs, we'll see the sign of permutations. But then if you look for syzygies among such sign of permutations, we get to the next level. So let me recall briefly this construction by Schur central extension. Well, it's generated by S1, S minus 1 as before, S for Sn, and the central element zeta, such that zeta square equals 1. It's an extension by z mod 2. It's the next z mod 2 here, satisfying by the condition that Si square normally was 1, now it is zeta. Si Sj would be equal to zeta Sj Si when I is disjoint from J. What I'm saying. And this the same braid relations. Si plus 1, Si equals Si plus 1, Si plus 1. So if we consider the true projective representations in which zeta equals by minus 1, so let's call it Sn tilde. So if you say C of Sn tilde by zeta equals minus 1, so then this looks like Si is J equals minus Sj Si. So, and that is, naturally is a superalgebra. Is naturally a superalgebra. In which this becomes instance of supercommutativity if we put degree of S equals to 1. So like supercommutativity. I'm simply mean that it's Z2 graded when if we put degree of S equals 1 mod 2. So then, of course, it's an algebra, it's the same. But then looking at this algebra, we see, oh, this algebra has a bunch of commuting elements. Whereas before, if we consider it's an ordinary algebra, then they don't commute. So in fact, a part, like in modern expositions of the central extensions of Sn, of projective representations, it's much more natural to consider representations of this as a superalgebra. This is simpler than the classical theory of Schur for representations. So let's call this algebra Rn. Representations R and as a superalgebra. That those are easier to catalog. So it's not very difficult in either case, but it's slightly easier in this case. So this is a sort of modern discovery. So now, having this in mind, I want to extract the first, I already erased this, what would be the next concept which would lead us into this direction. And this, we can say that this, let's call this part the supersymmetric monoidal categories. In the same way as we can pass from commutativity to supercommutativity. So let's try to do this on the categorical level. Let A be a k-linear category. K is a field. But it's not just k-linear, but will be a superlinear. So suppose that A itself is the category of representations of something super. So it is, let's call it superlinear. It means that we can tensor multiply objects of A with super vector spaces. Let's call tensor over the category of super vector spaces, which is graded by Z mod 2. Then in such a category, we have a natural categorical minus, which is the pi from A to A,